Okay, so good morning everyone. My name is Iñigo Asiáin and I'm gonna be talking about my research work with Domena Gasperio and Federico Mescia about new physics involving the Higgs boson. At least to me, one of the most interesting questions in particle physics is whether the Higgs boson is an elementary particle or is it a composite state. If it's the first case, if it's an elementary particle, it really takes a really interesting or special position in particle physics. Why? Because it would be the only spinless elementary particle that we know. If the other case is the reality, if the Higgs is a composite state, then we should be asking ourselves, what are the new strong forces that keep this condensate together? Of course, to start answering these questions, we need to start from the Standard Model, which is the theoretical framework that best describes particle physics so far. But it, as everyone else, it has some issues. First of all, from observation, it only explains around the physics of around 5% of matter content of the universe. The other 27% or so of matter content is a dark matter sector that we don't know much about or anything about. Also, it fails to describe massive neutrinos, but Tony will tell us about this after lunch much better than me. It also has some internal problems. We have the flavor puzzle or flavor problem, which is the inability of the Standard Model to explain why the masses and the mixings in the flavor sector, which are leptons or quarks, are what we know from the experiment. This leaves us with 22 free parameters in theory, which is obviously a problem. It also fails to describe why we have this little tiny source of CP violation in the strong sector. The theta of QCD, which is a dimensionless parameter, carrying out this CP violation is found in the experiment to be of the order of 10 to the minus 10. So why would a dimensionless parameter be that small? That's a fine-tuning problem. Another fine-tuning problem is the hierarchy problem related to the mass of the Higgs. When you compute quantum corrections of the mass of the Higgs, you can see that they are proportional to the cutoff scale of the theory. But if the Standard Model is to be complete, this cutoff scale is the Planck mass. So if we were to experiment and measure the mass of the Higgs to be of 100 GeV, then why it is much, much, much lighter than Planck mass? And of course, it doesn't accommodate gravity, but I'm too stupid to speak about this, so we shall leave it here. Okay, some of these problems somehow are related to the Higgs nature. So what is the role of the Higgs boson in the Standard Model? This Higgs boson was first predicted back in the 60s within a mechanism that gives mass to the electroweak H bosons, giving rise altogether to what we call the electroweak symmetry breaking sector. But within this mechanism, the Higgs itself and its potential are ad hoc artifacts. So where does the Higgs come from, and hence the electroweak symmetry breaking sector? It seems that we need new physics to explain about this. Okay. One of the possibilities is that this electroweak symmetry breaking sector is dynamically generated due to the spontaneous symmetry breaking of the vacuum of a new strongly interacting theory that lives at higher energies than the Standard Model. With these strong dynamics, if that's the case, we would be expecting new resonances at this new scale of spontaneous symmetry breaking. One of the most sensible ways to look for this new kind of physics, it would be vector boson scattering. Why? Within the Standard Model, we know that the Higgs unitarizes the scattering of longitudinally polarized electroweak H bosons. This means that the sum of these three first diagrams have a bad high energy behavior. The amplitudes grow with the energy. But once we add the Higgs resonance, this behaves well at all scales. So if now new physics comes into the map, it could modify the Standard Model HVV interaction and breaks unitarity again. So then we would be expecting maybe some new resonances to restore unitarity. Here I show an example of BSM amplitude, BSM model amplitude, of the scattering of longitudinally polarized electroweak H bosons, with this parameter A being the new HVV interactions. And here they are the only source of departure from the Standard Model. So when we see that A is equal to 1, the Standard Model value, the amplitude is well behaved at all scales. But if we depart even 1% from this Standard Model value, we see how the amplitude starts to grow with the energy. Okay. Okay. But if we don't know anything about this UV physics, high energy physics, then how can we study the problem? And the answer is through effective field theories. We will be using this bottom-up prescription that it doesn't need of a UV completion. We don't need to know about the high energy physics to know about its low energy consequences. This effective field theory breaks down at some energy scale depending on the low energy parameters of the theory, where perturbation theory is not reliable anymore. We will work under the assumption that there is a strongly interacting theory at some high energy scale compared to the electroweak scale, which is of a few TeV. This set of symmetries that, let's say, avoids or it doesn't take into account the electromagnetism, so there are no photons, and the electroweak gauge bosons W's and Z's are the same. The Goldstones will be taking the nonlinear realization of the symmetry, which kind of makes sense for these strong interacting dynamics. And we will be using standard model light degrees of freedom of the electroweak gauge bosons, their associated Goldstone bosons from the Higgs mechanism, and the Higgs itself, the light Higgs itself. An effective field theory with all these assumptions is called the electroweak Lagrangian, which is nothing but an extension of chiral perturbation theory, which was deeply used back in the 70s to study low energy QCD to the electroweak sector. This is nothing but it's built as an expansion in powers of the momentum, with this L2 being contributions that go as p squared, this L4 being contributions that go as p to the 4, and so on. At leading order, with this L2, we have these new physics interactions. This is the parameter A that I was telling you about in the other graph, in the other picture, and there another vertex with two Higgs in the final state. If we go to next to leading order, we have these new contact terms with 4 Goldstone bosons or electroweak gauge bosons, and also a contact term with 2 final states with Higgs. Okay, the idea is that the matter content that we don't know from the ultraviolet theory, from the high energy physics, is integrated out, and its low energy consequences, the footprints of this physics in the UV, are encoded in the so-called chiral parameters of our theory. However, this expansion in powers of the momentum, which is the electroweak Lagrangian, typically leads to violation of unitarity, and we cannot use this to make realistic predictions in the experiment. So some unitarization methods are required. There are plenty of them, but they have been proven to show the same qualitative results. They are all based on partial wave analysis, which is nothing but the projection onto the isospin-spin basis of our amplitudes, being this Ti, the fixed isospin amplitudes, which in the more familiar charged basis has this form. The good thing about our sets of symmetries is that since there are no electromagnetism, the electroweak gauge bosons W's and Z's are the same, and we only need this fundamental amplitude to compute the other ones, because the other ones are obtained by crossing symmetry. We will be using the inverse amplitude method, which was deeply used, again in the 70s, in pion-pion scattering, and it gave really good results. For instance, they could predict the Rho meson in pion-pion scattering. It has this form, and if we expand the denominator as a perturbation, we can see that this is nothing but a resummation of infinite chain of bubble diagrams. So if there is a pole in this amplitude, a resonance in this amplitude, it can be interpreted as a dynamically generated resonance with a mass and widths depending on the low energy parameters and quantum numbers I and J. If we want to interpret this resonance a la Wigner, we find the mass with the real part of this equation and the width with the imaginary part of this equation. Equation, I mean, where the denominator cancels is equal to 0. Okay, but from this EM amplitude, we need a full next to leading order calculation. There is one available now in the literature, but it's too complicated for our purposes. It takes into account 500 diagrams in custodial limit. There are no photons, and there's still 500 diagrams. So we'll be using a shortcut. We take the next leading order amplitude and we split it into its real and imaginary part. The real part has two contributions. One which is computed exactly with these A4 and A5 terms that I showed you with the contact terms from the L4 Lagrangian, and the other one is computed, which is the one loop contribution, is computed using the equivalence theorem. The equivalence theorem states that at really high energies, in this case compared to the electroweak scale, the longitudinal components of the electroweak gauge bosons can be substituted by its associated Goldstone, making this error here. The problem is now reduced from 500 to 90 diagrams, so it's a pretty good thing to do. And the imaginary part of this next leading order amplitude is computed exactly through perturbative optical theorem, which is a tree-level calculation that we can do easily. Some previous work used the extreme version of the equivalence theorem, where no W's or sets were allowed inside the loops. Physical W's and sets were allowed in the loops. They only used Goldstone bosons. They swept the relevant chiral parameters of the problem and looked for some vector resonances, which are this point that you can see in the picture for the real part of the vector amplitude or the mass, and the imaginary part where they can find the width of that resonance. We will be focusing on these 6 benchmark points. 3 of them, they have this chiral parameter A, which is the new HVV interactions, equal to the standard model value. And the other 3, they have this A value set to 0.9, okay? Both scenarios contemplate masses of around that oscillates from 1.5 to 2.5 TeV within the range of our effective field theory. Okay, what are our improvements from these previous works? We go one step further than the extreme version of the equivalence theorem. We allow physical W's and sets inside the loops. Now, instead of 94 diagrams, we go to almost 300, which is quite involved. And we have new parameters entering this vector amplitude, both in the renormalization and in the evaluation of the numerical evaluation of the finite part. We have these new contributions. What is the difference from what we had? In this case, this V cannot be a Goldstone boson. This is compulsory of physical electroweak gauge bosons. We didn't have that before, and we didn't need that. So the question is how the previously calculated vector resonances are affected. It is worth mentioning also that not only VBS, but we also computed this scalar final stage with WW going to HH and the elastic scattering of Higgses. It involved 1,500 diagrams, and well, this took my life for like very much time. Okay, so back to the question, how the previously calculated resonances are affected. We first want to investigate what is the effect of adding the electroweak gauge boson inside the loops. So these new chiral parameters are set to 0, but we set G, which is the gauge coupling of the electroweak gauge bosons, different to 0. And we can see that for every of these 6 benchmark points, we see variation of around 2–3%. Okay, this is just the picture of the vector amplitude, how you can perfectly see once you unitarize the resonance. Okay, now we want to investigate the effect of these new chiral parameters. If we set this A3 different to 0, then we have this new contribution at tree level that we didn't have before. what happens for these benchmark points here? The ones that are missing is because the masses of that resonance were out of the validity of the EFT. So for reasonable values of A3, we would be expecting, they are absent in the standard model, so we would be expecting that they have at least, at most, sorry, an order of 10 to the minus 2. But if we set these numbers, we see that they are not significant modification of the resonances we found before. And we find an inverse effect for positive and negative values. If we have positive values, the mass of the resonance increases, and we have negative values, they decreases. The very same picture we can see for this new theta parameter, which gives this tree-level contribution to the problem through an exchange of a Higgs in the S channel. And the very same we find for reasonable values of theta are not significantly modified, and we have this inverse effect for positive and negative values. So, what are our objective? We want, in the end of in the final steps of this work, we would like to make a Monte Carlo to make predictions about these vector or scalar resonances for the LHC via this physical subprocess that you can find in the LHC. Here you can put a scalar resonance or a vector resonance. Of course, the Higgs wouldn't be a wavy line, but just for easy representation. Okay, the conclusions are: effective field theories are powerful tools to explore high-energy physics in a model-independent way. We didn't say anything about the physics at the UV. Unitary amplitudes can help to constrain anomalous couplings by extending predicted resonances. An extended electroweak symmetry breaking sector typically have these resonances. We have found these resonances. And vector boson scattering is a promising channel to look for these BSM resonances. However, up to now, the LHC has not seen these resonances yet. Not 2 years ago, even more. I think 3 to 4 years ago, maybe I'm not updated, but there was this diboson excess at CMS with two sigmas. But we have to wait more and have more statistics. So thank you, everyone.
Okay, Iñigo, thank you. There is time for questions.
So, thank you for the nice talk. Finding the resonance would be certainly spectacular, but finding the resonance would be spectacular.
Yeah.
But if you don't find them, can you still use a current or existing or future LHC data to constrain the parameters of your effective theory, or
if these resonances are absent,
or you don't see them,
just to constrain the chiral parameters, I think you can, no, because if you don't find any resonances, you can set upper bounds on the. I have to think, but I think the answer is yes. That if you cannot find, no, I have to think it through. But sorry.
Okay, there is time for more questions. Okay, I have a question. I'm an astrophysicist, so I couldn't follow very well your talk. If you had to explain this idea how the Higgs boson can help us to go beyond the present status of physics or physical knowledge of particle physics, if you had to explain it to a kid, what you would say to him?
Okay. To a kid. Okay, we don't know the nature of this Higgs particle, okay, but we are really interested in if it's an elementary particle or composite state, if it's made of some of the things due to the presence of some new force. Okay. In fact, with this study, we cannot say anything about the Higgs being composite, but we are assuming that there exists this new physics that is strongly coupled, that is strong, and then it could be compatible with a Higgs being a composite state, but we don't know that from these kind of studies. So if there exists this new strongly interacting theory that is physics beyond the standard model, that is not explained within the standard framework, within the actual framework, the current framework. Sorry, yeah. So I think that is the point of this kind of investigations.
Thank you very much for this brief explanation. It's enlightening. Any more questions? If not, let's thank Iñigo again and all the speakers of the morning. And let's reconvene at 2:30, 2:30. Thank you very much.